This video is a continuation about packet switching, and in this video I'm going to be talking about a number of different queue models. I'm going to start out by describing a simple deterministic queue model. This is something that's going to help us understand the dynamics of many simple queue systems. It often works as a good way of understanding what's going on in the network. So here's a router, and as we know already, routers have to have queues in the interface to hold packets during times of congestion. And this is where the variability in queuing delay takes place. So if we can understand the dynamics, even just having a rough sense of the dynamics of that queue, it really helps us understand the end-to-end queuing delay and the dynamics of the network. So we're going to take a closer look at this, and we're going to just create a simple model. Here are the main characteristics of this queue. So I'm going to draw a queue like this. This is the standard way to draw a queue, showing where the packets will be stored. In that router queue, this is a 4-port router, so packets could be coming in from any of the interfaces into that queue, and then they will depart onto the outgoing link. We're going to say that that queue has an occupancy of Q of t, so at time t it has Q packets or bytes in it. It's going to be useful to think about the aggregate or the cumulative departure process. That is, all of the packets or all of the bytes that have departed up until some time t. Similarly, it's going to be useful to think of the cumulative arrivals, the total number of packets that have arrived up until time t. Finally, because the outgoing link typically has a deterministic and fixed rate, which is going to say has a fixed rate of r. So they're going to be the main parameters of our model. We can also think of a queue as being like a bucket full of water, and here's a simple example here. A of t is the cumulative number of bytes that have arrived up until time t. D of t is the cumulative number of bytes that have departed up until time t, and in this example they're going to depart at a fixed link rate of r. At any one time there may be some bytes that have arrived but haven't yet departed. They're the ones sitting in the bucket here, and the occupancy of that bucket is going to be Q of t. So this is like a simple model of our queue. It's just another way of thinking about it. We can draw the evolution of this as a function of time, and I'm going to try and sketch how this might look. So here are going to be the axes of my graph. As a function of time, we're going to look at the cumulative number of bytes. So remember, this is cumulative. I'm going to first look at the arrival process, A of t. Bytes tend to arrive as part of a packet, and they're going to arrive at some particular link arrival rate. So I'm going to draw what that cumulative arrival process might look like. It could look like anything, but here is the bytes arriving a packet. This is the gap between the first packet and the second packet. Here's a bunch more bytes arriving, a gap, maybe it's a long gap this time, and then a new packet arriving. So this is supposed to be a straight line, and this would be the arrival rate of the packet on the incoming link, and this is the number of bytes. So let's say the packet is of length p, the number of bytes of that first packet. Now let's look at what the departure process might look like. I'm going to try and draw that. I'm just going to label this as A of t, the cumulative arrival process. And then in yellow, I'm going to try and I'm going to sketch out what the departure process might look like. We know that the departure process is going to work at and operate at rate r. So at some point after that first packet has arrived, let's assume that it's a store and forward model. It doesn't matter. That's just for the sake of my example. So at this time here, the packet has arrived, and then we'll say, okay, it's going to depart at rate r. So that's going to be my gradient there. So that's rate r. That packet departing. At this point, there's nothing left, so we're going to wait until there's a whole new packet in the queue, and then we're going to depart again at rate r. That's going to be rate r, and so on. We're going to wait until a whole new packet, and it'll be at rate r again. So this might be one way in which it evolves. The point here is not the particular shape of this graph, but just to say you can easily sketch the arrival and departure process. And what this kind of a cool property of this is that we can immediately from this tell some nice characteristics of the system. First of all, we can immediately tell what the value of Q of t is, because at any one time, so if we were to pick a particular time, Q of t is the number of bytes that have arrived but not yet departed. So it's simply d of t minus a of t. I'm sorry, a of t minus d of t. So it's the number that have arrived minus those that have departed. So for example, if we were to take a line here down to here, so a vertical, it's supposed to be a vertical line, that value, that distance between the two of those is Q of t. So at any one time, it's the occupancy of that Q. Similarly, if we look at a particular byte that arrives, say at this time here, if we assume that all bytes arrive and then depart in the same order, then this byte, because it's this particular cumulative byte, we know that it departs here. So if we take the horizontal distance between these two lines, this is going to tell us the d of t, I'll call it little d of t, the delay through the queue. So this is a very useful model giving us an intuition. I often sketch graphs like this when I'm trying to understand the dynamics of a queue or the dynamics of a system. Okay, then to summarize, we can say that the queue occupancy, so queue occupancy, Q of t, equals, it's the ones that have arrived minus the ones that have departed. So a nice simple expression for that. And that d of t is the time spent in the queue by a byte that arrived at time t. So it's the time spent in the queue by a byte arriving at time t. And that's simply the horizontal distance between those two lines. Now, the assumption of this is always that it's first come, first serve, or FIFO. We also say first in, first out. In this context, those have the same meaning. So that's true. If the bytes didn't arrive and depart in the same order, then we couldn't make this statement here about d of t, because we don't know that we're referring to the same byte. Let's go on and look at an example now of how we might use this. So I'm going to work through an example. We're going to assume that every second, a 100-bit packet is going to arrive to a queue at rate 1,000 bits per second. In other words, this packet is going to arrive at a rate of 1,000 bits per second, and it's 100 bits long. We're going to assume the maximum departure rate, that was our R, is 500 bits per second. And the question is, what is the average occupancy of the queue? So just reading the question, it's not so obvious, but if we plot this in the way that I did before, I'm not going to try and sketch it because I want these numbers to be very clear. A of t shown in red here is the arrival process. This here is the packet arriving. It's the 100-bit packet arriving at rate 1,000 bits per second. So therefore it takes 1/10 of a second, 0.1 of a second to arrive. The maximum departure rate is 500 bits per second. It's slower. So our departure rate, d of t, the rate here is that the gradient of that is 500 bits per second. So that 100-bit packet is going to take 0.2 of a second in order to depart. In the previous example, I showed it as a store and forward of each packet. Here I didn't, and that's just a choice, and I just made that choice when answering the question. The question isn't clear as to which way it is. So we can now see the time evolution of Q of t, which is the vertical difference between those two lines, and the delay of an individual packet. But the question is, what is the average occupancy of the queue? Well, let's look at how we might solve that. I'm going to write this out just so that you have a clear record of this. So the solution is this. During each repeating 1-second cycle, the queue is going to fill at rate 500 bits per second for 1/10 of a second. So that was my arrival process here. Then it drains at 500 bits per second for 0.1 of a second. Over the first 0.2 of a second, the average queue occupancy is therefore 0.5 times 0.1 times 500 equals 25 bits. The queue is empty for 0.8 of a second every cycle. That's from here to here. And so the average queue occupancy, Q bar of t, is 0.2 of a second when it's 25 bits and 0.8 of a second when it's 0. So the average queue occupancy is 5 bits. Continuing with our theme of simple deterministic queue models, I want to explain why it is that small packets can reduce end-to-end delay. You may have been wondering why we can't simply send an entire message in one packet. Why is it that we have to break messages down into smaller packets? There's a very good reason for this, and I want to explain this in terms of the end-to-end delay. So on the left, I've got an example of a message of length r that's being delivered from end to end. And this is going through 3 routers, R1, R2, and R3. And I'm just showing, as we did before, the delay across each link in terms of the packetization delay and the propagation delay over the links as it makes its way across the network. We already know the expression for the end-to-end delay for this. It's simply made up of the sum of all the m over ri's. This is the packetization delay. And then the sum of all of the propagation delays over the links. So we've seen this before. If you look at the one on the right, we can see that the message has been broken down into packets of length p. So I've broken that same message, it's the same length as before overall, this is the message, but I've just broken down into packets of length p. So the packetization delay over the first link is p over r1. And so now the end-to-end delay is this expression here, p over ri for the packetization delay on each link, and then li over c for the propagation delay. M over p is simply the additional time for the ones who arrive at the end. Strictly speaking, there should be m minus 1 over p because it's the remaining packets. I'm going to assume that m is much bigger than p, so that's basically the same. M over p times r3, the packetization delay of that packet, of that set of packets over the last link. But the most important thing here is that you can see what's going on. In this case on the left, the whole message has to be transferred over the first link before it can start on the second link. Whereas over here, the first packet goes and then is transferred onto the second link while the first link is carrying the second packet. So we've got a pipelining effect. We've got parallelism over the links. And so therefore the end-to-end delay is going to be reduced. Over a long network with very big messages, this will make a very significant difference. And so the end-to-end delay can be reduced by making the packets smaller. Let's look at this simple example here. I've got a number of flows, n flows, or n packets coming in on n external links, all running at rate r. I've got a packet buffer corresponding to the output queue of the router, and then an outgoing link that's running at rate r as well. Clearly, if all of those ingress links were running at the full rate r, then the output link would be overwhelmed and would start dropping packets very quickly. And in fact, there would be a rate of n times r coming in and a rate of 1r going out. So we'll be dropping them at a rate of n minus 1 times r. But because of the statistical multiplexing and the burstiness of the arrivals, we can potentially get away with this if the average rates are sufficiently low. So in general, we say the reduction in rate that we need at the egress compared to the ingress is because of that statistical multiplexing, and we call that benefit the statistical multiplexing gain. We never know what it's going to be precisely because it's going to depend on the particular arrival process of packets. And temporarily, if there are temporary oversubscription to the output link, the buffer can absorb those brief periods, and so a bigger buffer is going to absorb bigger and longer periods when the aggregate rate happens to exceed r. But because the buffer has a finite size, there's always losses that can occur, and that's just a fact of life in packet switching, nothing that we can do about that. Let's look at a couple of specific examples here. See the top part at the top here, I've got a communicating an arrival process A into this router buffer that's being drained at rate C. and a separate one that is going through a router that's arriving at rate B, and being drained at rate C. And I'm showing over here on the left-hand side the rates as a function of time. And you can see here that the peaks and troughs don't exactly line up, so that if we take the sum of the two, or the sum of these two flows, then we can expect there to be some statistical multiplexing gain. Let's have a look at what that might be. Of course, I've made up these numbers. These are just to give us an example. But if we take A plus B here, that was the rate of A plus B, and that's the line in pink. That's this one here. You can see that their combined rate, the rate of the combined flows, R, is quite a bit less than 2C. In other words, less than the sum of the two peaks. So in this case, we would say the statistical multiplexing gain equals 2C over R. It's the benefit that we're getting from summing the two of them. We can actually come up with a different definition, and some people use a different definition for statistical multiplexing gain, because in this case you can see we didn't actually take advantage of the fact that there is a buffer. We're not using that to buffer any temporary rate that exceeds R. So one definition could be that for a given buffer size B, the ratio of the rates that we need in order to prevent packet loss is the statistical multiplexing gain, and that generally will be a lower rate because we can absorb the change. So for example, in this case, imagine that we were to serve it at this rate R prime instead. So we'll call that R prime, where R prime is a little bit less than R. So long as the amount that we need to buffer here and here when the rate exceeds R prime can be accommodated by the buffer, then we're okay. And so in this case, for the buffer of size B, we might say that instead the multiplexing gain is 2C over R prime, which is a slightly larger number. Okay, so two definitions of statistical multiplexing gain. One where we don't consider the buffer, and one where we do. So, in summary, often we can use a simple deterministic model of a queue to understand the packet dynamics in a network. And I'd encourage you to do this. It gives a very good intuitive understanding of what's happening in the network. I often use this myself. Second, we learned that we can break messages into packets, or rather the reason that we break messages into packets is because it lets us pipeline the transfer of packets from one end to another and reduces the end-to-end delay. Finally, statistical multiplexing lets us carry many flows efficiently on a single link, and this is one of the prime reasons that we use packet switching. Okay, that's the end of this video.